Welcome to Algebra 2. Today we've got section 11.5, making inferences from sample surveys. So for a few sections now in chapter 11, we have just been looking at what makes a quality experiment. How do we sample? How do we choose our sample? How do we set up the controls in the experiment or the study that we're doing? And then do we have any biases or anything that may be affecting the outcomes? Now we get to actually take that data, the result of our study, our survey, our experiment, and we get to use that to describe and project those results to hopefully tell us something about the entire population. So let's take a look. So there are two main branches of statistics, descriptive and inferential. The descriptive statistics, it's just like the name says, it's used to describe or summarize data that has been collected. Inferential statistics takes that sample and then you're making a conclusion about a bigger population. Okay, so one is describing what you found, one is using the statistics to make an inference about a larger population. All right, now naturally, when we're working from samples, we're not going to get a 100% accurate description of the population based on how big of our sample, how big our sample is. So there is a margin of error involved, and this is just a way of saying that, hey, we only have we have a relatively small sample, so it's likely that our error is going to be pretty great, that the whole population might vary more than what we calculated. The margin of error formula is a very simple one. It's plus or minus 1 over the square root of our sample size. That's it. And all that is saying is that the larger the sample size, think about that, that's going to make the denominator of this fraction bigger and bigger and bigger, which means our margin of error is 1 over that bigger and bigger number. It's going to be smaller and smaller and smaller. And that margin of error, it does say plus or minus in front. That's because our estimate could be overshooting or undercutting the actual population. It's designed to kind of give us a range that we can trust as we infer what our sample is saying about the population. So pretty quick formula. That's one of the few formulas we've actually had to learn so far here in chapter 11. And that leads us into our first example. So here we've got 35 U.S. households in a survey, and the incomes from those 35 households are shown in this table. It says to estimate the population mean mu. All right, so our population mean, well, based on our sample, we are going to use the mean as a descriptor there. So this part, our population mean mu is going to be the sum of all of these entries over 35. So I'm just going to write the sum of all of our x's over the number of elements. In this case, that's 35. And when I calculate that out, yes, it's going to take some time to type in all of these numbers, but when we calculate that, we get $51,029. Okay, and if we wanted to find the margin of error within this sample, you can see we've only sampled 35. This is not part of the question. It's just kind of, I don't know, extra calculations that we can do. We would do plus or minus 1 over square root of 35 to find our margin of error as a percentage, So $51,029 plus or minus 1 over root 35%. Or converted into a percent. Okay, so we found our mean, and it's just like you would expect. This could be, a 7th grade math problem. Average all these numbers up. That's all we're doing. Then I've added in a little extra down here. It says estimate the population proportion P of household incomes that are over 60,000 and B under 20,000. So we're going to use our sample to come up with an estimate of the proportion of the total population. So all we're going to do is we know that for part A here, we'll do that one next. Let's just count how many of our 35 households had incomes that were over 60. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So the population proportion P that were 60,000 plus is equal to 13 out of those 35, or roughly 0.3714. Okay, so that is the proportion of households within our sample that had that income. We could project that then into our population. Again, there is a margin of error there as well, and we're going from a sample to an entire population. Letter B, now we want to find the population proportion that is under 20,000. So we're going to do the same thing. How much of our sample was under $20,000? I've got 1, 2, 3. So that is 3 out of 35 in our sample. So the proportion we would expect for our population should be around 3 over 35, which is 0.0857. All right, now we're trusting that this random sampling is truly random here. And, you know, when you look at the entire population, that if we were to conduct an actual survey there, like a census, then that may change a little bit. But this is a good approximation based off of our sample. Okay, so the math has really been kind of just what we would expect. Our second example, your teacher lets the students decide whether to have their test on Friday or Monday. The table shows the results from 4 surveys of randomly selected students in your grade who are taking the same class. These students are asked whether they want to have the test on Friday. All right, so what we see is our sample size, when we've only asked 10 people, 8 of them say, yes, let's have the test on Friday. That's 80% of the votes. When we've sampled 20 people, asked them, 12 said yes to the quiz on Friday or test on Friday. That's 60% of our votes. So part A says, based on the results of the first 2 surveys, do you think the test will be on Friday? Well, looking at these first 2, we do have a majority of voters. Over 50% of voters are saying, yes, let's have this test on Friday. So for part A, yes, over 50% of voters want the test on Friday. Okay, and then letter B says, based on the results in the table, so not just the first 2 surveys, but the final results in the table, do you think the test will be on Friday? So once we've surveyed 40 people, only 18 of them said, yes, let's have this test on Friday. That's only 45% of the votes. So by the time we've finished our survey, no, now under 50% of voters want the test on Friday, and that's a minority. So chances are you will get the weekend to study, and that test will be given on Monday. Now, that's a likelihood. That's just based on this sample size. If there are like 300 students taking this class, who knows? When that sample size gets higher and higher, we may see more and more voters say yes for the Friday test. But as a result of this table, we would think that no, the test will be not on Friday. All right, so our third example, employee engagement is the level of commitment and involvement an employee has towards the company and its values. A national polling company claims that only 29% of U.S. employees feel engaged at work. You survey a random sample of 50 U.S. employees. Excuse me. Letter A says, what can you conclude about the accuracy of the claim that the population proportion is 0.29 when 16 employees from your survey feel engaged at work? Well, we would compare our sample to what this polling company is saying. So for letter A, our results from our little survey show that 16 out of 50 employees feel engaged at work, which is approximately, well, it's exactly 0.32. So we could say that since 0.32 is roughly 0.29, the whoever took the survey or whoever made the survey is being accurate. So that 0.29 is an accurate mark. Our survey is agreeing with it. Letter B, what can you conclude about the accuracy that the population proportion is 0.29 when you survey 50 employees and find that 23 of them feel engaged at work? So now our little survey is giving us 23 out of 50, which equals 0.46. Now that's a pretty significant change from our 0.29 that this polling company is giving us. So we would think, since 0.46 is, what's a good way of putting this, is relatively far from the 0.29 that the polling company gave us. 0.29 is inaccurate. Oh, we should probably stick the word likely in there. We're conducting a small sample as opposed to this huge national polling company. So we should add the word likely. Maybe we have a company where its workers are all, a higher majority of this company feel engaged at work than in other companies. So that word likely kind of helps safeguard our answer. But we're still comparing our survey results to the results of this big national polling company. Is it close or is it not? All right, example 4, find the margin of error for a survey that has the given sample size. Round your answer to the nearest tenth of a percent. So here we're using our little margin of error formula. So for number 14, that margin of error is going to be plus or minus 1 over the square root of 6,400, which equals plus or minus 0.0125. And as a percent rounded to the nearest tenth, that's plus or minus 1.3% approximately. Same process for number 16. So you can see we had a pretty small margin of error when we had that many people in our sample size, right? 6,400, that's a pretty large sample, so our margin of error is going to be pretty small. In number 16, here we have 750. Run that through the same formula, and I get plus or minus 0.0365, which as a percentage is roughly 3.7%. So you can see having a smaller sample space has increased our margin of error because that small sample has a chance of not being indicative of the whole population. Right, and our final example, in a survey of 1,022 U.S. adults, 76% said more emphasis should be placed on producing domestic energy from solar power. Letter A says, what is the margin of error for the survey? Okay, well, 1,022 U.S. adults, there are many, many, many more adults in the population than that. So we're going to have some error in using this relatively small sample. Our margin of error is going to be plus or minus 1 over the square root of 1,022. And that gives me 0.0313 approximately. So our margin of error is plus or minus approximately 3.13%. Then letter B says, give an interval that is likely to contain the exact percent. So if we go with this 76%, that's the result of the survey, if we apply our margin of error, we get a range that is likely to contain the exact percent when we look at the whole population. That's what the margin of error is incorporating here. So what we're going to do is, for our lower bound, we're going to take that 76% and subtract away 3.13%. And for the upper bound, we're going to take 76% and add that margin of error. And so what we get is a range that goes from 72.87% to 79.13%. So when we incorporate those margins of error, it is very likely that the exact average for the entire population falls within that interval. All right, that does it for section 11.5. Here, take a look. Some of the problems are ABC problems. You can see that number 9, we just want you to do parts A and B, and then number 25, we just want you to do parts A through C on that one. But again, now we're taking our results of our surveys and stuff that we've evaluated and that we've analyzed a little bit, and now we're able to look at the numbers and take that and apply it to a population, either descriptive or inferential. That does it for 11.5.